Good morning, everyone, and I hope now that you can hear me. Welcome to the IBM Qiskit live quantum seminar series. Today, I'm thrilled to roll out our first Q&A special seminar series with the amazing folks you can see here alongside me. Olivia and I will moderate and take questions from you live in the chat. So feel free to post your questions as we discuss in the chat. We'll keep this fairly informal. And before we get to it, we always like to start with, where's everyone tuning in from today? Feel free to post that in the chat. And I can already see folks saying, thank you, Caleb, Caleb says, hello, Qiskit is always the best thing to watch during lunch. That means a lot. Thank you. Folks are tuning in from USA, India, Germany. It's, as always, a worldwide audience, so I'm thrilled everyone could make all the different time zones. Thank you very much. California, Mexico, Spain, Japan, Israel. We'll be having a Qiskit hackathon in Korea soon, so hopefully see some of you there as well. We have folks from the UK and Cambridge and so forth. And I think, Olivia, maybe we should get started and dive in, and I'll let you introduce or help introduce everyone.
Okay, great. Thanks, Zlatko. Hi, everybody. I'm Olivia Lanes. That was Zlatko Minev. We are from IBM Quantum, and this is the Qiskit seminar series. Like Zlatko said, this is our first informal Q&A today. So I thought the best thing to do would have some of our illustrious past speakers go around and briefly introduce themselves. And then if anybody has any questions, please put them in the chat, and we'll do our best to moderate them. If they're for a specific person, you can note that as well. But why don't we just first start with some introductions. So Jack, do you want to go first?
Sure. Thanks for the opportunity to be here, first of all. It's a pleasure. My name is Jack Harris. I'm in the physics department at Yale University. I'm an experimentalist. I don't work at all in quantum computing, but I do work on areas that I think are immediately adjacent, maybe immediately underlying, maybe immediately hoping to benefit, ride around on the coattails of quantum computing a little bit. My group works in the field called quantum optomechanics, where we try to use the tools of quantum optics, single photon detectors, lasers, and the like, and extend that kind of control to the motion of relatively large, massive, solid or liquid objects. From the kind of nuts and bolts side, we don't use microwaves. We use optics. All of our control is with telecom wavelength photons. And the kinds of objects whose motion we're trying to control with this light might be conventional micromechanical oscillators, but we've also gotten really interested in what kinds of motion you can study in superfluid liquid helium, which of course has just one amazing property after another. So that's my research and its connection to quantum computing, maybe broadly defined.
Awesome. Thanks, Jack. Sophia, how about we go to you next?
Sure. So hi, everyone. I'm also very pleased to be here. Thank you for the invitation to IBM. My name is Sophia Economou. I'm a professor of physics at Virginia Tech. I'm a theorist. I work on various aspects of quantum information science. So I work on quantum algorithms. I'm especially interested in near-term variational algorithms, which have applications, as I discussed in my seminar a few months ago, in quantum chemistry and many body physics. There's also optimization algorithms we're interested in my group. And then on a kind of a different subtopic, we're also working on quantum communications, especially with applications in quantum networks. And there we're interested in coming up with ways to design protocols for the generation of large-scale entanglement, especially for photonic states. And then finally, we're interested in quantum computing and especially more practical aspects like quantum control, coming up with good ways to control qubits, and those include superconducting qubits and spin qubits, and a lot of the techniques are actually transferable between different systems.
Awesome. All right, how about we go to Guillaume next, because you're next on my chat list.
Sure. So I'm Guillaume Verdon. I'm a research scientist and product lead at Sandbox at Alphabet, which is a team within Alphabet working on quantum, AI, and all sorts of other things. I guess principally I work on hybrid between quantum and classical machine learning. And broadly, I'm just looking at how can we import techniques from physics into AI and techniques from AI to help doing physical sciences. So previously, I started the TensorFlow Quantum project at U Waterloo, and that's what was my way into Google. And yeah, since then I've been a champion for hybrid quantum classical machine learning. So that's my background.
Awesome. Okay, and last but not least, we have Antonio.
Thanks, Olivia. Yeah, I'd like to, again, thanks everybody, Zlatko, for inviting me again to speak at this panel here. My name is Antonio Mezzacapo. I'm a research scientist at IBM Quantum, and my main focus nowadays is doing research on quantum algorithms, especially algorithms that target interactive many-body systems, which include quantum chemistry systems. I have some interest in machine learning and how machine learning techniques can be optimally combined with quantum computing to address different type of problems. I worked in the past on quantum software, and also in my early years in device modeling, and how can we make better gates and better qubits, and build better and better quantum superconducting processors.
Awesome. Thanks, Antonio. Looks like Jack might have had some difficulties, but hopefully he'll be back with us in a minute. So I should have mentioned, I guess, before we got started, that please feel free to ask any questions you might have for our panelists. They don't have to be technical questions. They could be non-technical questions as well. If you want to talk about careers or maybe the outlook of where we see the field going in every respective, subject, that would be really cool, I think, to discuss as well. But maybe the first question I'd ask is, since we last had all of you on the Qiskit seminar series, has there been any new or interesting updates to your research since then? Anyone who can just chime in here at any point, please.
Can you hear me?
I can hear you.
Yes.
Am I actually back? Can you see me? You said that I had disappeared.
Yeah, we can't see you, but we can hear you.
Okay, that's weird. My little video light is on, and it says I can see myself in the window. Okay, well, but I will just go ahead and tell you a tiny bit. Since my last Qiskit talk, we've learned a lot more about detecting individual phonons. So these are sort of the particles of sound, or the individual energy quanta associated with the vibrations of a solid object, or in our case, liquid object, and really trying to build up a toolkit that's almost analogous to the single photon detection capabilities that we're used to with visible light or infrared, but instead to have those capabilities with phonons, the individual particles of sound. And we've got that working to a pretty fair degree, and are starting to learn how to characterize the quantum aspects of sound in small bodies of liquid helium.
Cool, that sounds super interesting. Anybody else have any new recent updates?
I guess I'll go. Yeah, I mean, these are all like spoilers for March meeting. I think full spoilers will the full story will come out when we get to that conference. But I guess my talk was on quantum probabilistic generative models, which is combining a class of machine learning models called probabilistic machine learning models, which are generative models for probability distributions, and combining those with unitaries that are leveraging quantum computers. So it's really these hybrid models to create a variational class of states, which is more general than just simply starting with a pure state. It's called a mixed state, right? And so we've been looking at all sorts of applications of what you can do with these? And I guess the answer is it's harder to find what we can't do with those because we're still looking for what we cannot do. So we're very excited by this research direction. I guess like more on the more technical side, I can say that we've been investigating something called information geometry, which I think is of interest to various people working in variational algorithms. I've seen all sorts of papers pop up in recent months. Information geometry for optimizing variational models is kind of looking at sort of second order information in the landscape. Really, it's kind of using a notion of distance and state space and pulling that back to parameter space. And so, how much, if I move this parameter, how much does my state output by my variational model change? And you could tune your gradient descent steps and your optimizers using that information. And I guess, depending on your model, it's always a challenge to estimate what is called the quantum Fisher information metric, which might be of interest to, it's also a quantity used by experimentalists for tomography and so on. But I guess some of the progress there is that we've extended the natural gradient estimation to these hybrid models. So you can consider the whole parameter space of a hybrid model and get natural gradients for the whole thing. And of course, that speeds up the hybrid optimization. So you can kind of steer the whole ship as kind of one unit using natural gradients. So it's exciting, but that's kind of just a sneak preview of kind of the progress we've made there. It's been heads down for the past year on these things. So we're very excited with what we're going to release March meeting and going forwards in 2021.
Yeah, maybe I can also jump in. I talked about variational quantum algorithms as well in my seminar. So since we've made quite a bit of progress in improving our algorithms, and the main focus so far for us has been coming up with a good ansatz, and especially problem-tailored ansatz for variational quantum algorithms. So, unlike ansatz that have a lot of expressibility and span a lot of the Hilbert space, we're actually interested in coming up with ansatz that are very tailored to the particular problem you're trying to solve. And that has advantage of not searching more than you need to around the Hilbert space, around the solution space, and also avoids some technical issues like barren plateaus. So we've made quite a bit of progress in that. Our paper's available on the archive, and we also have March meeting talks, so I'm not going to go into technical details. And then on our optimization algorithm, we actually have now strong evidence that what our algorithm is doing, which is kind of on its own coming up with its tailored ansatz, has connections to a very different topic, which is called shortcuts to adiabaticity. So we think that in some sense, what QAOA, the algorithm, is to adiabatic evolution, perhaps our algorithm is to shortcuts to adiabaticity. So those are the things that are exciting for me compared to what I talked about, kind of following up to what I talked about in Qiskit.
Thank you, everybody. Oh,
I guess I guess I can give a little spoiler to what we are going to present at the March meeting. I mean, to the extent that that's been communicated in the abstract for the conference. So what we're thinking along these lines of, again, seeing whether classical computations can play in the field of quantum computing, and how how classical computing can really help, for example, like reducing the quantum computing overhead required to run a certain problem. And so what we're gonna talk about there is basically a method to simulate many-body system for which is a chemistry system in the particular example that we addressed there, using only half of the qubit required. So a system that would normally take 10 qubits, we basically show how to simulate that with half of the qubits. And to do that, we make of course, we need some assumption on the model. So yeah, if you want to know the details of this, just look into our talk at the March meeting. And then again, yeah, recently I've been thinking a lot of myself too about hybrid quantum classical models of computation. So I think we'll see a lot of new ideas sparking from that direction.
Thank you, Antonio, and thank you, everyone. Also, thank you guys for posting the questions. We're getting to those from the chat, and there was definitely a good number of questions about hybrid classical and quantum algorithms as well. So maybe let's start there. And one of the questions here was, how far along have quantum algorithms come? You know, sort of from your point of view. You know, where is the stage of development? You know, how specialized versus general are they compared to something, say, like the Grover algorithm? So maybe somebody would like to give a perspective or say a few words on that. Just from your point of view in terms of, I know it's a very broad question. And,
Can we restrict to variational algorithms?
let's start there.
All right, sure. Yeah, so I guess when was QoA first introduced? It was 2015, 2016, something like that. But it took maybe a year and a half before the community really realized that variational algorithms are kind of the nearest term type of algorithms that are really interesting, and that's because you use kind of a quantum computer in the loop to search over short quantum programs that do a certain task in general, right? And so for the near term and likely the medium term, in my opinion, variational algorithms are kind of the main game in town. So it's been, you know, very interesting to see kind of an explosion, really a Cambrian explosion of all sorts of variational algorithms over the past few years. And you know, now I guess we're kind of considering how to take, you know, state-of-the-art methods that have been shown successful on the classical computing side, machine learning, and kind of combining that with the power of variational algorithms. And that's personally the area of research very excited about. But yeah.
Yeah, and that's interesting. Maybe there's a question streaming in here. And what about the limits of variational algorithms? I think people are very excited about them, but you know, where are the trade-offs or where are the potential limits as well? You know, whoever wants to. I know Guillaume, maybe you want to take that first.
Maybe yeah, I can take this one. So first of all, I'd like to say something about variational algorithms. I don't think of them as, you know, relegated to this NISQ era. So for example, if we like suppose that we have a fault-tolerant quantum computer in 20 years, whatever, 10 years, and somebody wants to run phase estimation, right? So phase estimation is not the solution to every problem, right? So the state for phase estimation has to be initialized in a good way. So right, so the system has to start with a decent overlap with the ground state in order for the phase estimation algorithm to be successful. So variational algorithms could be one of the way of preparing that initial state. So, you know, I don't see all the research that people are doing on variational algorithms as being relegated, confined to the NISQ era, or I see a future for them even in the fault tolerant world. Now, what are the limitations of those? It's the limitation of any algorithms, I guess, that's trying to tackle a QMA complete problem. So there's no guarantee that you're ever going to get to the solution of that problem in polynomial time, either with a classical or quantum computer. So there's always some heuristic component in these algorithms, right? Otherwise, something revolutionary will happen in computational complexity, right? Modulo, that kind of stuff. So I guess that's a limitation. And how do we design better heuristics? How do we design a better heuristic which is targeted to the problem that we want to solve? This is, it's a challenge that in some way we share with classical algorithms. So there are classical variational algorithms, and they have the same problem. So how do you tailor your heuristic to the specific target problem that you want to solve?
I'd like to jump in there. I think the quantum space before, a lot of simulators and software and open access to quantum computers were a thing. I guess when I started in undergrad and in grad school, everybody was just doing theoretical scaling proofs. Big O notation, which is you kind of ignore the prefactors of your algorithm and you check asymptotic scaling. And I guess quantum computing was really much kind of a monoculture of like prove your asymptotic scaling, or you don't get invited to the party. Whereas now it's more kind of an applied, or I guess, well, there's still a lot of complexity research. It's just that the applied quantum computing community has kind of taken the front stage by storm, I guess. But if we look at classical machine learning, right, the general problem of learning a distribution is also, NP hard, extremely, doesn't scale well. But then, of course, that doesn't stop just about every company or most companies to try to implement AI algorithms at scale in production, and it has huge uses in real life, right? So I guess variational algorithms, it's easy to get hypnotized by them. We're still searching within the broad Hilbert space of states, which is still an exponentially large space, but we're kind of tracing a path, a submanifold that's n-dimensional for n-dimensional parameter space. So I guess to me, I think what's going to be important is going from what we started with, which was, I don't know how to parameterize my hypothesis, so let me just parameterize a very general unitary, which are these quantum hardware efficient ansatz, which are very much suitable for NISQ. And now we'd rather start engineering more. I have a good idea of the submanifold, or the spots in Hilbert space, which is extremely large space, where my physical states or my data states lie, right? And so you only want to parameterize the submanifold where you think the interesting stuff is happening. And actually, even though we talk about the Hilbert space being exponentially large, if you look at any physical state in nature, it actually lives in a tiny sliver of the Hilbert space, right? Of the sliver of physical states that have correlations arising from time evolution under local unitaries. So I guess the work that we have ahead of us as physicists, mathematicians, computer scientists, etc., is to start kind of using our physics knowledge to engineer better priors over this hypothesis space of states. And once we do that, then we've kind of compressed our search over the Hilbert space, and we've I think that's how we're going to achieve quantum advantage for variational algorithms. So I'm sure a lot of people here have some work that is related to some of these comments I've made. So I'm going to leave the floor to other speakers now if they want to comment on that.
Yeah, I just wanted to agree with points made both by Antonio and Guillaume. So one point was, that the separation between VQEs and NISQ and kind of fault tolerant is not as harsh maybe as people kind of led on to believe. And, it's maybe because historically there's kind of two communities, but I think the interesting research will be kind of in between, and it's not going to be a phase transition from, a few qubits and bad gates to suddenly, the perfect quantum computer. So there's going to be a lot of interesting and exciting research, I think, going forward. And like Antonio said, VQE could be the starting point of phase estimation algorithm. And in phase estimation algorithm itself, there's different versions of it where you can trade off measurements with gates. So that in itself is not, And there's already that going on there. And then in Guillaume's point, a lot of the very well working classical algorithms are heuristic, right? So the fact that some problems work exponentially hard in chemistry doesn't stop quantum chemists or physicists from coming up with good, computational solutions to solve the many-body electronic structure problem. And there's been a lot of progress in that. So yeah, I just wanted to kind of chime in and reinforce those 2 points.
Okay, great. I think that was a really good discussion. This next question is sort of going to change topic a little bit, but I think it's important. Somebody in the chat wanted to know how you guys keep up with all of the literature in the field, if that's even possible. Archive publishes, hundreds of papers on quantum computation, quantum communication stuff every week. So how do you guys, as professionals in the field, keep up with it? And maybe, I don't know, maybe we can start with Jack on this one. We can still hear you, Jack.
Yeah, and maybe I'll interject the comment here that will be slightly interesting and provocative from Alan, who said, "Don't read the literature, write the literature." So, take that as a would.
I was gonna start there. I'm a little bit humbled that you directed this question towards me. I am bad at keeping up with the literature. I remember once someone saying to me that there was a famous quote, "You can either read the literature or contribute to it, but not both." And I don't think that's really strictly true, but I thought it was interesting that at least someone famous had said this and that this idea got out there. I devote a small fraction of my time to staying up, and that's bad. Like, I feel guilty. I think I'm missing out on things. I have limited, physical resources, and I don't, I definitely prioritize trying to keep my group moving forward and learning about the things that strike me as interesting and trying to kind of stumble into new things a bit more than following the literature. It's not a recommendation to anyone else. Whatever Frank Zappa said about drugs, sort of what I'm saying. This is not necessarily the approach I would advocate.
Maybe can say something. I mean, I think, of course, like nobody can read all the papers that show up every day in full detail, right? In full detail. So I think it's good to develop the ability of having like a broad picture of what's going on. Maybe, read the titles, read the abstract, try to develop a sense of like, what do you think it's relevant? What do you think it's important? What do you like? So all these, this is something that you develop as a researcher as you go on in your career, right? So I guess for a student, the amount of literature could be very like daunting, right? The things that appear every day on the archive, especially now that we have seen this explosion of the field. So I would say just pay some effort, just try to develop some like kind of like critique of the field, like your sense of what is important and what is not, and read what you think it's relevant for you, and only read maybe the abstract, the conclusion. Try to guess what the paper is talking about without reading all of it. And last but not least, talk to people. So I think talking to researchers, it's an awesome way of having your question answered. It's an awesome way of getting the essence of research of a paper, of what you're trying to understand. And so just don't be afraid of sending emails to researchers and interact with them. That's probably the fastest way of being up to date with what's happening. So yeah, I think Alan's comment, it's a bit too far, too far from on the other side of the spectrum. I think as in most cases, there's a sweet spot between not reading anything and like spending your whole time just keeping up with it. So it's my 2 cents.
I guess I can.
I now wish I had said what Antonio just said.
I think another way to do it is, to have a group of people. In my case, of course, I have my own group. But if you don't have your own group, you can have a community of your peers where you share some kind of, maybe Slack or some kind of way to communicate. And then not everybody reads every paper, but there's some kind of dynamic journal club going on. Even if it's not in depth, you can still, mention this paper came out, I read it, and this is the summary. I try to get my group members to read the papers instead of me and send me a quick summary. So that's a nice way to do it if you can.
Yeah, that's good. Maybe a very interesting quick follow-up here, and this is just like a 30-second answer. But do you guys pay attention to the email domain when you get an email from an unknown address, or the academic domains are more valuable in the sense, like if you're trying to communicate to researchers, would you use your academic or your Gmail? Does that matter? Or just very random question, but kind of follow up on the communication aspect.
I guess.
Yeah, you go.
Yeah. I guess I read, any email that's not blocked by a spam filter or anything like that. In general, I guess it's easier for the wider community to reach via like Twitter or something. I like to interact with any question, even from, I don't look at the academic credentials when I get a question. I just kind of look at the question itself. If it's a very long wall of text that is going to take some time investment to get through in my inbox, then that's a different story. But I guess I guess I would look at the domain, but I'd probably read it anyways and see if I want to reply regardless.
Thank you.
So long as the font doesn't change too many times.
Comic Sans only. Comic Sans only. We only accept that. Changing gears completely, maybe for a minute, since we spent some time on algorithms, there were a lot of questions sort of centered around photonics or also optical systems in qubits. So maybe we can touch on that just really for a bit. Quantum networks, quantum communication, interconnections, photonics. Maybe Sophia and Jack would like to talk a little bit more about that, either on the progress of the field or what the state of the art is, what are the largest scale photonic entangled states that we have. I'll open it up to you folks to take that.
I'll let Jack go ahead.
That's not really my particular area, so the answer is I don't know. I do pay careful attention to not so much like the size of entangled states in like terms of the size of the Hilbert space, but I do pay attention to like the physical size of objects whose dynamics are in some way entangled or in which quantum effects have been observed. And since that's what I know a little bit about, that's just what I'll answer, even though that's not what you asked.
Would you tell us about that?
Yeah, so this is a distinct question, and it's sort of, I think a lot of people have this notion that it would be really interesting to understand if quantum mechanics applies to macroscopic objects, and if not, why not, or if there's any subtleties there. And that's like a deep intuitive concept that like a freshman, first year undergraduate student would understand that immediately. But this word macroscopic does not have any sort of strict platform independent definition. So we have this intuitive notion that this is an interesting question, but when you try to boil it down and really quantify what you might mean by macroscopic, there are a bunch of different answers that are potentially interesting. One is, I think, closely related to what you said, which is kind of like the size of the Hilbert space over which the quantum state has some interesting structure. Another way in which size or macroscopicness appears in quantum mechanics might be the inertial mass of the object that we're talking about, or the number of fundamental particles that are in some meaningful way involved in creating this state. And that's still like a little bit tricky to quantify because at the end of the day, when we do quantum mechanics, what we talk about are degrees of freedom. And people in LIGO who are studying the motion of 10-kilogram slabs of glass that like you can see it's big. If you dropped it on your foot, it would break your toe. And they would say they see quantum effects in the motion of this object. But you can say that really what they're seeing is quantum effects in one of the normal modes of this massive system, which is 1 degree of freedom, which is a small Hilbert space. So why is that any more macroscopic than anything else, than a qubit or a 2-level system or a defect spin somewhere? And it's a legitimate question and involves some context-dependent answers, some of which might be interesting from the point of view of quantum gravity. So if you regard a 10-kilogram object as a source of deformation in space-time geometry, and you take its center of mass degree of freedom and put that in a superposition of states, that might have some meaningful connection with the quantization of the gravitational field, in a way that, say, taking a 10-kilogram object and creating a quantum superposition of some very high-order phononic mode, which is sort of another, like, one could say that if you see quantum aspects in the phonons of some high-order acoustic mode of some very large object, is that more or less macroscopic than seeing corresponding quantum effects in that object's center of mass motion? Depends what you're interested in. From the point of view of coupling to the gravitational field surrounding the object, there might be a difference, but from the point of view of quantum information, there might not be. This is a very long-winded way of saying it really depends on how you define macroscopicness. And I think you just sort of have to be clear about how you're talking about it. It also, but maybe to come to a quick question in terms of proper entanglement that goes beyond maybe 2-mode squeezing and would involve Wigner function negativity or some real quantum information processing resource, the largest objects in which such things are seen, I think we have kind of just crossed the line into picogram scale, cubic micron scale, nanomechanical devices. I'm thinking specifically of the work by Simon Groblacher and Marcus Aspelmeyer. Though even there, like, the degree of control over these quantum resources is pretty modest. I mean, I think this is a rapidly moving field. I think real, tangible quantum interference, the record might be held by the matter wave interferometers of Marcus Arndt with relatively large organic molecules, tens of thousands of protons. So in terms of that notion of macroscopicness, I think that's where the field stands.
Yeah, that's an interesting distinction also between matter and light, because there was these Schrödinger cat states with 100 plus photons and so on, but that's quite different from picograms of mass.
That's a really interesting question from an algorithm standpoint, is, how far do you have to zoom out on a quantum system before the effective description becomes classical, or the effective entanglement between degrees of freedom that are renormalized is kind of low enough so that you could
scrambled,
or like kind of sparsified or downsampled, right? In physics, you have renormalization, which is looking at the effective physics at different scales, and I guess my hope is that we're very focused on algorithms for, like, patches of systems, a little grid of spins. But of course, for practical, if I want to simulate a whole block of a material, it's not going to necessarily fit on a single device. So is there a way where we could take inspiration from deep learning to kind of zoom out and have kind of patchworks of simulations to kind of understand much larger systems? And that's dependent in a sense on the theory of classical emerging, or classical statistical mechanics emerging from quantum, if you renormalize or zoom out enough. So I think it has parallels with this discussion of macroscopic effects that Jack just started. Yeah.
I would slightly disagree with that. I mean, I think like, anytime anyone uses the word macroscopic, you should just stop them right then and there and ask them to define what they mean. And there are many different legitimate answers, and one of those would correspond to what you're talking about. But I think people who some people, it's just worth noting that there are some people who kind of regard this question of macroscopic quantum mechanics as somehow being associated with mass and gravity. And that's really distinct, I think, from information processing advantages. Not more important or less important, just as important. Just this word macroscopic is like a great way to kind of stumble into misunderstandings.
I'm kind of worried now because I use the word macroscopic quantum superconducting circuits a lot. So
you should, I would once you're aware of this, I would do that to sort of bait people, to draw people out. Because like at some point, someone should say, well, what do you mean by macroscopic? It gives you a chance to kind of construct a teachable moment, I think.
I mean, I guess one can like formalize that from a quantum information point of view, right? So so a classical system, I guess you can define it as a system which cannot keep coherence, right? Quantum coherence between the different states. So maybe you can see it how mixed it is, and the like being mixed. Like we know that we can correlate there's a correspondence between the rank of a mixed system and how it interacts with its environment, right? So like formally, you can say the more a subsystem, the strongly a subsystem interacts with its environment, the more it's going to be mixed if you just look at that subsystem. So that would be a formal way of defining it. And this is there's a lot of consequences, of course, in the various physical, this description of this. For example, interaction with the environment could come through thermal photons or whatever you can specify this description to the various physical systems that you're dealing with. But
I think what you're talking about.
Sorry, I was gonna say that then, Antonio, by your definition, you would not classify superconducting qubits, for example, as macroscopic, whereas there it's an example where you have, a very large number of electrons behaving coherently, and it's, I think, kind of an important example of what Jack, like in the kind of spirit of what Jack is talking about, in kind of forcing this very large system with many degrees of freedom to behave coherently.
I think that's a great point, and I know there was kind of this discussion, a little bit contentious discussion some years ago about like how many electrons there are in a superconducting qubit participating in these states. And all I would say is those discussions are great, just keep in mind that the word macroscopic has no strict definition, I think, in physics. And we use it ad hoc as we use language all the time. Just be willing to say what you mean by macroscopic, and be cognizant of the fact that there might be a lot of different, valid, interesting questions around that. Regarding the point about sort of mixed states, I think what you're talking about is a different concept. And I somehow in my mind, like I do try to keep in mind two orthogonal axes, one of macroscopicness, which we've just sort of talked about, and the other of quantumness. So
yes, I was definitely talking about the quantumness axis, yeah. not the microscopic axis.
And I think these are, again, quantumness. People would offer differing definitions. I think your notion of like how much coherence, how mixed is the state, is a totally good one. But again, for different applications, for different specific questions, people would apply different metrics there. And I would just say, I would love to have this conversation. This is a great setting in which to have it. Like, I sort of think about these questions that people talk about as having these two independent axes, like how big, how quantum. And both of those are a little bit ill-defined, but in a context-specific way, you can usually give a precise definition.
And Sophia, I wonder on that note, we were touching on large-scale photonic entanglement. Is macroscopic a concept that gets used in that context, or?
I have not heard it be used in that context. I think it's more of a kind of condensed matter originating term. For the photonics, you at least for discrete variables, you built these states kind of starting from small systems. So I don't think that notion transfers, but it definitely transfers to phonons, like Jack was talking about, where you're trying to cool a system, and these are native kind of excitations in the system. So maybe it's more relevant there.
Can I add maybe like a little provocative statement? So in that like two-dimension diagram, where would you put the whole universe, right? Is the whole universe a coherent, isolated, big system, or what it is, right?
I'm not qualified to attempt to answer that question.
So I guess that would be in the far top right part of that diagram.
If you could demonstrate somehow the entire universe actually does undergo quantum coherent evolution, I don't know what the status of that question even is.
There's the Hubble radius, though, right? So we're constrained to a subregion of the quantum field, so we're stuck in mixed state land, right? And so, it's hard for you to know if you're in a global pure state from just having access to local mixed state. So I guess it's going to always be very hard to answer, is there a global pure state wave function for the entire universe, which I think some theoretical physicists like to play with. But for experimentalists, I guess it would be difficult to design an experiment to test that. But it's an interesting philosophical question for sure. On the notion of quantumness and scale, and this is actually a segue to some of the stuff we're actually investigating with quantum probabilistic generative models, is that, if you go at different scales or different temperatures, of course, or different parameter space regions of various Hamiltonians and condensed matter systems, you have different amounts of quantumness. And for a practical kind of workflow quantum advantage for quantum simulation, maybe there's systems in nature that if you zoom out sufficiently enough, let's say you're looking at like proteins, right? Maybe there's like very subtle quantum effects, but you're zoomed out enough where there's not enough quantumness happening at that scale, or there's not too much. So you could only add in quantum complexity with low depth circuits to a classical representation. So I guess what we've been investigating has been kind of sweeping over various parameter spaces and sweeping over how much quantum depth versus kind of classical model complexity you need to even just represent quantum states. And I guess the dream is that instead of kind of having no quantum advantage and then suddenly, boom, you could simulate the universe, like in the show Devs or something. It's going to be more a continuum where we can go to more refined scales, lower and lower temperature, more and more quantum, or systems that exhibit higher quantumness over time as quantum computers can, sample with high fidelity from deeper quantum circuits. So I guess that's part of the research program we're pushing. What is the minimal amount of quantum computing do we need to have an impact on, say, being able to predict protein folding, which obviously would have immense applications, as we are possibly painfully aware, everyone here, during the past year and such. So yeah, that's an interesting question of kind of what is quantumness, what is macroscopicity, specifying that, and then operationalizing that through quantum algorithms.
Yeah, thank you. And maybe to kind of wrap up this discussion, this is very interesting. I think this is an open questions, and one thing I learned is I'll be very thoughtful or careful now when I use the word macroscopic. So thanks, Jack. I'll think twice about using it. Maybe just for my personal curiosity as well, Sophia, we didn't quite get to answer that question before we move on to the next topic of what the state of the art is, or where the largest photonic entanglement is.
Yeah, so I'm more familiar with the discrete variable, so I'm not going to attempt to discuss continuous variable photonics, which is maybe Guillaume knows something more about, and he can chime in. But with discrete variables, just to give a little bit of context, people are trying models of computation that are somewhat different from the circuit model of, for example, superconducting qubits and trapped ions, where the idea is that you build upfront a highly entangled photonic state, which contains basically the necessary entanglement, and then you make measurements on it. This is called measurement-based quantum computing. Very recently, PsiQuantum put up a variation of that, which they call fusion-based quantum computing. In both models, you need to create resource states, which are photonic entangled states, and then the computation proceeds by making single qubit measurements. And in the fusion model, you also do Bell measurements between the photons. So from the published literature, the record is on the order of 10 photons from Jianwei Pan's group in China. I'm not going to quote an exact number, but it's on the order of 10. I don't know if PsiQuantum has, beat that record with results they haven't published yet, but it's quite possible they're pushing that approach. And then maybe I should also mention that similar resource states are actually of interest in quantum communications and quantum repeaters and networks, where people talk about the quantum internet. And there again, you want to create large-scale entangled photonic states, which you can use to transfer information and to create entanglement that is distributed over the network. And this has also connections to quantum error correction and photonic encodings, error encoding. So there's actually connections between photonic quantum computing and quantum networks and communications.
Yeah, it's interesting how far both the readout and single photon generation fidelities have come of those systems in the last few years. But I think maybe, Olivia, we should change gears here to the next question.
Yeah, so this next question was asked a couple times in the chat, so I want to make sure we get to it, but it's definitely changing direction, so just as a heads up. So the question is, I have been seeing some recent calls not to build quantum computers for ethical reasons. Is there a valid reason to believe that this quantum technology is too dangerous of a tool for us to use or to ethically handle? Could anybody comment on this? Yeah, let's start with you, Guillaume.
That was a quick hand.
Yeah, I mean, it's an interesting question. We're still exploring what exactly the power and the advantage of quantum computers is over classical computers. I don't think that we'll see a day where you reach a certain threshold of a quality of a quantum computer, and then suddenly overnight it just eclipses using supercomputers for, say, protein folding or whatnot. I think it's going to be kind of a hybrid system, and it's going to be kind of a slow phase in of a quantum advantage, and eventually it makes practical economic sense to use a quantum computer. It's not going to be like, oh, we've summoned a demon or something, like some people think about the singularity. So I would say it's the same ethical questions. At least to me, the main area of quantum advantage I'm focused on is kind of quantum simulation and quantum machine learning. And then there it's the same ethical questions as being able to simulate, biological or chemical systems, right? There's a trade-off between democratization, ease of access, and of course, if it's very easy to simulate and design drugs, and it's open to all, then you never know what sort of adversarial agents, how people could leverage that. So I guess to me that's kind of the main area that people should examine. But at least for now, it's too early to, in my opinion, to anticipate how quantum computers are going to impact these areas. But it's I absolutely do not think we should stop building quantum computers at this point, or in the future either, right? It's not, once you've discovered a technology, the genie is out of the bottle, and then it's a question of, safety engineering. People have, now there's AI safety as a field. how to control these systems. But I think we're still very far from that in the quantum space. So please just keep on doing the engineering for now, I guess is my opinion. Yeah.
I think it's, I kind of like second some of the things that Guillaume said, but I also think that it's important to having this debate, like keeping the debate alive, because look at what happened with AI, right? So suddenly I think like people had the feeling that the technology like went much further than what the ethics debate behind it could have followed that, right? So I think like sometimes you don't know like how fast, how quickly a certain field is growing. So I think it's it's healthy to keep the debate alive and think about these things as the technology grows. So like in the time that we're living, it may seem that this fault-tolerant quantum computer, it's an idea which is years away, so we wouldn't like to worry about these things. But when it comes, it may come sooner than what we think. And when it comes, I think we should be ready. And some of the applications of quantum computing are shared with other technologies. So the debate could be imported from those areas. Some other don't. So some applications are disruptive. So maybe there should be a specific targeted debate for those ones.
Thank you. And this is an interesting question we have. It's for any of the panelists. If you could take a 6-month or 1-year period and work on a different project, not what you're working on currently, what would you choose? And maybe you could tell us a little bit about why you might choose it, or what are some of the things that you might consider doing. You could channel your oh, I see several hands raising, so whoever wants to go first.
Guess I'll go. In my case, I think something called neuromorphic computing is very interesting to me. I think with all this quantum engineering, I think we're kind of inadvertently restarting the interest in analog systems or analog computer engineering. And before you get to a very quantum system that exhibits superposition and entanglement, is there a sweet spot where we can use kind of the modern tools that we have to engineer analog computers that would kind of actually be the replacement for classical digital computers for certain applications such as AI? And to me that's a very interesting question. Of course, as a physicist, we're always interested in phrasing everything as physics. So but yeah, that would certainly be what I would spend a year on easily if I weren't doing quantum computing.
Jack, do you have something on your mind as well?
Yeah, maybe a little bit close. I would say like this connection between computation and physics. There are like some things that I find deeply puzzling about it. And if I had some extra time, it would be spent on just learning more about mathematical logic and foundations of mathematics and how it applies potentially to physics or the physical universe. And I still feel like a little bit confused about the way that formal systems that mathematicians and theoretical computer scientists use, about how well they really jibe with physics, Newtonian mechanics, quantum mechanics, which are formal systems in their own regard. And I think I'd like to understand the connections between them better.
Yeah, Sophia or Antonio, does one of you, or maybe Sophia, do you want to just offer some thoughts on what directions you might consider?
I mean, I think personally, what I would do is going back to the early question, read the literature more. If I somehow was given a year free time, that'd be awesome. In terms of topic, maybe I would start thinking more, learning and thinking more about quantum error correction, especially for near-term applications and specific systems. So I'm very interested in kind of bridging more formal aspects of quantum information with more practical. And that I find an interesting direction.
Yeah, and Antonio, what do you think?
Yeah, I guess I have to pick something which is totally unrelated to what I'm doing right now. So
You don't have to, but you're certainly welcome to.
yeah, I guess, I mean, certainly the interplay of quantum information science with basic physics is interesting. Like some people are moved in that direction, right? So what is the quantum informational black hole and stuff like that? So that could be fun to explore.
Maybe I'll just interject here and ask Zlatko what he would do if he had, 6 months to a year off from work. What project would you be pursuing in that time? Unrelated to what you do now.
Yeah, unrelated to what I do now. Oh man, there's a long list also, I think. Yeah, there's a long list. Well, I think a little starting closer to home, actually I would go and explore more on even more deeply some of the quantum measurement business. There's some ideas there, and in terms of maybe closer to what Jack said about when things get larger, when things get entangled and separated, and actually looking at the measurement process, the way by which it occurs underneath that. That's maybe a little too close to home. Then kind of moving further away from that, actually software architecture principles, engineering design is something I enjoy a lot as well. So that's something I've been brushing up on. It's not physics per se, but it's an essential tool. So I found that very helpful. And then that leads into really just doing classical machine learning and AI. Actually, I find that just satisfying as a fun project. Building and constructing there, and image recognition in particular, vision recognition is something very fun to play with. And then I guess on the more physics condensed matter side, I think I would go back and read all of Steve Gervin's latest book on condensed matter and dive deeper into understanding all of the different definitions of Cooper pair operators and so forth. So that would be the other side. Good. And then I think, Olivia, we could take maybe one more question, or we're close to the hour here. I know there was a question about a good starting point for people to get into the field. I don't know if we touched on that, or if we wanted to turn them back to you and also ask you actually what you would spend 6 months to a year on first.
Oh, yeah, I guess I kind of set myself up for that one. Well, I mean, on the physics side, I'm also really interested in the measurement questions. So maybe if I wasn't doing so much simulation stuff, that would be something that I would be interested in looking into. What is, by a strict definition, what is a projective measurement? What is a weak measurement? Where do we draw the line? Those are some questions I'm interested in. But then if I guess we sort of leave quantum behind, I'm recently become interested in statistics and how humans interpret data and make decisions based off of priors. I guess that's something that I'm sort of just as a hobby right now interested in. And I would love to do a project sort of with that in the future. But yeah, why don't we leave me alone for a minute and ask maybe one more question to wrap up here.
There was a question that just popped in the chat in terms of new folks coming into the field and getting into fields the kind of fields that you've got into. What would you should we take? I think that would be a good question to take, right? To say what advice would you give to people? You've come very far in your career trajectory, and you have a lot of experience, a lot of successes under your belt. You've seen a lot. The field is today very different. There's a lot more resources in a sense, but kind of looking at that and taking that into account, someone who is younger or getting into the field just now, where could they start, or what would you do if you were in their shoes? And maybe let's start with Sophia first.
That's a tough question. I think it depends a lot on kind of where you are. You know, if you're have you started undergrad yet or not, or you know, you're in high school. So I think there's very different resources depending on where you are. I would say, assuming that you have some STEM background already, kind of going and learning the basics is very important. You know, not try to go directly to, you know, some very difficult and applied thing. On the other hand, now that there's all these resources available, at the same time, you can also play directly with, you know, quantum processors, for example, IBM's quantum experience. But I would say do both. You know, don't just run circuits without knowing at all what you're doing. Learn the basics and the fundamentals.
Yeah, and maybe to narrow down the question a little bit, we can say that this is somebody who's let's say post-bachelor level, just to kind of hone in, because it is a very broad and open question.
I think
go to the Qiskit website and
Yeah, then there's a lot of, you watch the summer school lectures, summer school lectures. Guillaume, what about you?
Yeah, I would say there's been kind of proliferation of resources for people getting into the field. You know, I think you know, these open courses, these summer schools. You know, there's a lot of resources online, and I think you know, I wouldn't. Some people think if they do some online courses, you know, it's not quite the same as a formal education, but you know, 5 years ago, I did an open. I'm going to admit, I did an open course on Coursera about machine learning, and now it's my job, right? So it's okay to you know, start with that. I wouldn't say you have to take a graduate course formally at a university to get going. I would say it depends what you want. If you want to just get going as soon as possible, there's probably an efficient path to learn just what you need to get by. But I would say have a very broad intake at the beginning and then specialize later. Just how we train deep neural networks, you want to generalize and transfer learn. So the broader your data set and the more instances where you see a concept appear, especially quantum information itself is extremely broad, the more you'll be able to generalize. So, you know, learn quantum mechanics, quantum field theory, condensed matter if you can, and then quantum computing as well. And you'll see there's actually a lot of cross-fertilization of ideas there. So it's not just about importing code and running it, which sometimes is tempting with all these, you know, great frameworks that are out there. But I would say really try to form a solid base if you want to be in it for the long run. Yeah.
And
I love that you related that back to a neural network.
TensorFlow. And maybe there's a follow-up here in the comment chat box about mid-career changes, and maybe I'll address this one towards Jack. I know Jack has been very good at constantly evolving and diving into, you know, headfirst into new fields, you know, like the superfluid helium as opposed to membrane in the middle. You know, those are very different things in a sense. So maybe Jack, you could offer some thoughts for, say, a physicist or computer scientist, somebody who's mid-level career, who is thinking about a change into a more quantum focused field.
Yeah, it's a great question. I think it depends so much sort of on where you are now and what you're thinking about. I don't have a great general answer, but there are resources for supporting things like that sometimes, depending on where you are. So in a university, sometimes there are little grants or bridge grants, leaves, sometimes certain kinds of leaves that can be used for scholarly work. Sometimes there are deans or department chairs or managers who are sympathetic to that kind of thing. But beyond that, I don't have a fantastic general suggestion, except, you know, to be true to your curiosity and do it where you can.
Maybe to add to what Jack said, I think it also helps a lot to work with someone who's already in the field, and you would have to contribute something as well. So, for example, if it's someone who works on algorithms, maybe you come from you have domain knowledge, like let's say you're a chemist, you can bring in something from your domain. This is just an example, but I think that's the best way to learn.
Yeah, I agree. Collaboration and conversation make a really huge difference. It's hard to do things in isolation.
Absolutely.
Yeah, I mean, I think that's really good perspective. Like, you know, in general, we like to say there's no magic pill, right? It's not like you can just read one book or, you know, take one course and then you're an expert, you're in the field, you know it now, right? Like it's a very gradual process, a neural network, like we were saying before. I really like that analogy. I'm going to use that from now.
Good. Well, I think seeing that we are about 10 minutes over, and I'm already, by the way, you can't see the comments, unfortunately, but I'll relay them to you. People are saying thank you. So there's a few comments. So I think folks in the viewership here and the audience have really appreciated your time, your thoughts, your comments. So thank you very much for taking our invitation for this Q&A first seminar. Thank you also to everyone tuning in. And maybe we'll just open it up to a couple of final words or thoughts or comments that folks would like to say. We can turn it over to Guillaume first.
Yeah. Thank you for inviting me. It's always fun to get to interact with the community. You know, it's one of the perks of this this era of you know, live streams and video conferences, which are very popular. It's really great format, I think. And yeah, I guess if I'm going to advertise, check out the March meeting. And I guess in the shorter term, there's an event that both IBM and Sandbox are sponsoring, which is the QHack.ai hackathon, which is a quantum machine learning hackathon. So it's going to be a cool event for the quantum machine learning community. And I think signups are still open. So I would invite you to check that out. That's my blurb. Yeah.
Antonio, would you like to offer some thoughts?
Yeah, again, thanks again for inviting me in this this nice conversation. I'd like to thank everybody that tuned in, and we like the passion that people are showing towards quantum computing. It's great, and it's great to see the community motivated and growing. And we think that this kind of panels, what we are doing here, this kind of conversation will help even more, you know, strengthening the community and informing people. So I just hope this was helpful.
Thanks, Antonio. Maybe Sophia, if you have any last words or recommendations.
Yeah, no, just thanks a lot for organizing this. And I think IBM has been fantastic in building community and continues to do this. And it really makes a difference to people. I've seen that from the graduate student applications we had this year, you know, how much it has helped students around the world, you know, hear about quantum, do hands-on things. So yeah, thank you.
Thanks, Sophia. We really appreciate that. And Jack.
Yeah, just very quickly, thank you to you guys for organizing this. The Qiskit seems like a really nice resource, and just in general, the chance to share and have these conversations is a really big service. It's nice to be part of it. Thank you.
Well, thank you, Olivia, for helping me co-host. Thank you to all of our panelists. Thank you, everyone, for tuning in. This video will stay recorded, so you can go back and rewatch it. Find us or follow the folks here on Twitter or their website. Stay in touch. And thank you, everyone. We will see you Friday, 12 p.m. Eastern Time next week.
Thank you, guys.